It is 14:30 hours on February 9th, 1942. The location is Pier 88 on the North River in New York City. The temperature is 26 degrees Fahrenheit and the wind is sharp. Locked inside the ice at the pier stands the largest and most expensive moving object ever built by the French Republic. She is the SS Normandy, but the paint on her hull now reads USS Lafayette. She is currently undergoing a frantic conversion from a luxury ocean liner into a troop transport capable of carrying 15,000 soldiers to the European theater. She is the fastest and most elegant solution to the logistics problem of the Second World War. But in 12 hours, she will be a dead loss, lying on her side in the mud. The catalyst for this catastrophe is not a torpedo or a saboteur. It is a single spark. Deep inside the Grand Salon, a workman is cutting the last of the steel stanchions that once supported the heavy Art Deco lighting fixtures known as the glass fountains. The oxyacetylene torch hisses and spits a shower of sparks. Under normal maritime protocols, the deck would be clear. But in the haste of wartime conversion, the ballroom is filled with bales of burlap and thousands of kapok life vests stacked in piles. Kapok is a fibrous vegetable material that is extremely buoyant but also oily and highly flammable. One spark lands in the center of a vest pile. The kapok does not smolder, it explodes. The fire races across the varnished woodwork of the salon, consuming the luxury paneling that was never stripped out. The ship's advanced fire suppression system has been deactivated for the conversion. The only defense is water, and that water will become the executioner. The New York Fire Department responds with massive force. Fireboats surround the liner and begin directing high-pressure streams into the burning upper decks. From a firefighting perspective, this is the correct tactical decision to suppress the thermal energy. From a naval architecture perspective, it is a death sentence. A ship relies on a low center of gravity to remain upright. Stability is dictated by the relationship between the center of gravity and the center of buoyancy, which is known as the metacentric height. When the center of gravity is below the metacenter, the ship is stable and will return to vertical if pushed. When the center of gravity rises above the metacenter, the ship becomes unstable and will capsize. By late afternoon, the fireboats have pumped over 6,000 tons of water into the upper superstructure of the liner. This is an enormous mass of fluid introduced at the highest possible point in the hull. The physics are undeniable. Every gallon of water pumped onto the promenade deck acts as a lever raising the center of gravity of the vessel. Furthermore, the water is not frozen in place. It is free to slosh across the wide open spaces of the ballroom and dining halls. This phenomenon is called the free surface effect. When the ship lists slightly to port, the water rushes to the port side, instantly shifting the center of gravity further in that direction. This creates a feedback loop. The list invites the water, and the water increases the list. By the early hours of February 10th, the list has reached 40 degrees. The harbor master watches as the lower portholes on the port side touch the surface of the river. Once those openings submerge, the river itself begins to pour into the hull. The buoyancy battle is lost. The ship rolls slowly and violently to port. The massive funnels smash into the ice and water. The hull shudders and comes to rest at an angle of 80 degrees. The fires are extinguished by the river, but the strategic asset is gone. The Navy has lost a troop ship and gained a shipwreck that blocks critical pier space in the busiest harbor in the world. The engineering team, staring at the metal carcass, now faces a problem that appears strictly impossible. They must rotate a vessel that weighs nearly 80,000 tons without destroying the pier she is resting against or the city infrastructure nearby. They cannot lift her. They have to trick gravity into correcting its own mistake. They must rotate a vessel that weighs nearly 80,000 tons without destroying the pier she is resting against or the city infrastructure nearby. They cannot lift her. They have to trick gravity into correcting its own mistake. 79,280. That number is her gross tonnage. It measures enclosed volume, not weight. Her true mass is her displacement. Tens of thousands of tons of water she pushes aside. In the river, that distinction matters. Because buoyancy does not care about marketing numbers, it cares about weight. No crane in 1942 can lift a meaningful fraction of that displacement. So they do not fight the ship with machines, they fight it with gravity and buoyancy. The geometry of the disaster adds a second layer of impossibility. The ship is currently resting at an angle of 80 degrees. She is not merely listing, she is flat on her side. The port side promenade deck is buried deep in the river bottom and the starboard bilge keel is pointing at the sky. A salvage operation usually involves patching a hole and pumping out water to restore buoyancy. But here, the orientation of the ship has turned walls into floors and floors into walls. The internal architecture of the ship has been rotated 90 degrees relative to gravity. Staircases are now horizontal obstacles and corridors are vertical shafts. But the most lethal variable is invisible. It lies beneath the waterline, buried in the dark water of the Hudson River. The salvage masters Captain B. E. Manseau of the United States Navy and Captain John Tucker of Merritt Chapman and Scott discover a terrifying anomaly in the hydrographic surveys. The ship is not resting on a uniform surface. The river bottom at Pier 88 is composed of two distinct geological zones. Near the shore, under the bow of the ship, there is a hard rock ledge. Further out into the river, under the stern of the ship, there is deep, soft river mud. This creates a structural trap known as the rock fulcrum. The bow of the ship is pinned firmly against the unyielding rock ledge. The stern of the ship is floating in 40 to 50 feet of semi-liquid mud. This means the ship is effectively a giant steel beam balanced on a single hard pivot point. This geometry dictates the entire salvage strategy. If the engineers pump the water out of the stern too quickly, the rear of the ship will rise due to buoyancy while the bow remains pinned on the rock. The result would be a catastrophic torque force applied to the midsection of the hull. The keel would snap. The structural spine of the ship would fail and the vessel would break in two. If that happens, the salvage fails instantly, and the pier is blocked forever. Conversely, if they do not generate enough lift in the stern, the mud will refuse to let go. The mud of the North River is a viscous mixture of silt and clay that creates a powerful suction effect. It grips the huge surface area of the submerged hull like a vacuum seal. To rotate the ship upright, they must generate enough force to break this suction, but not so much force that they break the ship across the rock fulcrum. It is a precise balancing act involving 80,000 tons of steel and millions of gallons of water. The engineers realize that brute force is suicide. They cannot pull the ship up, they must rotate her in place. They have to induce a rolling motion that mimics the capsize in reverse. To do this, they must remove the water from inside the hull, but they must do it with surgical precision. They need to lighten the ship just enough to reduce the weight on the rock, but not enough to float the stern violently. They are not treating the ship as a boat anymore. They are treating it as a complex hydraulic cylinder. But before they can pump a single drop of water, they must do something even harder. They must make a capsized ocean liner airtight. They must seal the ship against the river while working entirely underwater in conditions that would terrify a claustrophobic miner. You do not lift a 79,000-ton ship. You convince it to lift itself. This is the central logical paradox of the Lafayette salvage. The entire operation is not a feat of strength, but a feat of control. The salvage team is not fighting gravity with cables and cranes. They are manipulating the laws of buoyancy with pumps and valves. But to control the buoyancy of a vessel, you must first make it watertight. The USS Lafayette is a steel carcass riddled with hundreds of openings. Before a single gallon of water can be pumped out, every one of these holes must be sealed against the crushing pressure of the river. And this work must be done by divers operating in an environment of total blackness. The water of the North River in 1942 is not water. It is a cold, thick soup of mud silt and raw sewage. Visibility is zero. A diver cannot see his own hand in front of his face mask. He cannot see the hull of the ship he is working on. Every single task must be performed by the sense of touch alone. The divers are not explorers. They are human-guided robots programmed to perform mechanical tasks in a lethal sensory deprivation tank. They are lowered into the blackness with blueprints of the hull memorized in their minds. They must feel their way along the cold steel plates, counting rivets and weld seams to locate their targets. There are 356 main portholes that are submerged on the port side. Each one is a gateway for the river to flood the ship as soon as pumping begins. The engineering solution is a custom-designed wooden patch. These are not simple plugs. They are heavy timber shields built on the surface and lowered down to the divers. Each patch is fitted with a thick rubber gasket. In a stroke of wartime ingenuity, these gaskets are manufactured from the rubber matting stripped from the ship's own decks before the fire. A long threaded bolt known as a strongback projects from the center of the patch. The diver must guide this bolt through the porthole by feel. Then a second diver working inside the capsized hull in equally black conditions must find that bolt feel for the threads and tighten a nut, pulling the patch into a watertight seal against the outer hull. This process is repeated 356 times. It is a slow, grinding marathon of underwater construction. But the portholes are only the large openings. The salvage plan identifies over 4,500 smaller holes, from scuppers to ventilation intakes, that must be sealed. Divers use thousands of custom-shaped wooden wedges, hammering them into place like corks in a bottle. They seal the main sea chests, the massive intake valves for the engines, with cofferdams made of steel and concrete. They are effectively building a second skin on the ship, one patch at a time. The work is physically brutal and psychologically punishing. The divers navigate a maze of debris, sharp metal, and shattered glass from the fire and capsize. A torn diving suit means immediate exposure to the contaminated water, and the risk of infection is absolute. After months of this relentless work, the outer hull is sealed. The ship has been transformed from a sieve into a container. The engineers have a vessel they can control. The pumps can now be connected, and the process of dewatering can begin. But the math reveals a new crisis. Even if they pump every compartment dry, the ship will not rotate. She is still too top-heavy. The fire destroyed the light aluminum superstructure, but the heavy steel promenade and boat decks remain. The center of gravity is still dangerously high. Sealing the hull was only the first step. Now they have to perform radical surgery on the patient. They have to cut the weight off the top of the ship before they can even think about rotating the bottom. The equations of naval architecture are unforgiving. Even with the hull sealed against the river, the USS Lafayette remains a prisoner of her own geometry. The center of gravity is dangerously high. If the salvage team attempts to pump her dry in her current configuration, she might rotate, but she will likely roll too fast and snap her keel on the rock fulcrum. Or worse, she might roll past vertical and capsize onto her starboard side, trapping the pier beneath her. To regain stability, the engineers must execute a massive program of weight reduction. They must decapitate the ship. The order is given to strip the vessel down to the promenade deck. This is not a delicate disassembly, it is industrial surgery. Gangs of cutters swarm the exposed starboard side of the hull. They slice through the massive steel funnels, the masts, the bridge structure, and the officers' quarters. Over a period of months, 5,000 tons of steel and machinery are cut free and lifted away by floating cranes. The iconic silhouette of the Normandy is erased. The upper decks that once hosted the elite of Europe are reduced to scrap metal on a barge. This aggressive reduction of top weight lowers the center of gravity, bringing the ship back within the envelope of theoretical stability. But lightening the ship is only half the battle. They also have to control the water that remains inside. The greatest danger during the righting process is the free surface effect, the same hydraulic phenomenon that sank the ship in the first place. If the water inside the hull is allowed to slosh uncontrollably from side to side during the rotation, it will destabilize the vessel. The engineers need to divide the massive internal volume of the ship into smaller watertight compartments. This allows them to pump out specific sections in a specific sequence, giving them fine control over the buoyancy. But the original watertight bulkheads of the ship run transversely across the beam. Now that the ship is on her side, those bulkheads are horizontal floors. They are useless for stopping water from moving forward and aft. The salvage team must build new bulkheads inside the submerged hull. This requirement forces the divers into the most disorienting environment of the entire war. They must enter the capsized interior of the liner. Inside the hull, the world is rotated 90 degrees. Gravity pulls in the wrong direction relative to the architecture. A corridor that once ran the length of the ship is no longer a hallway. It is a vertical shaft plunging 40 feet down into the dark. A doorway is no longer an exit, it is a hole in the floor or a hole in the ceiling. The divers call these the vertical corridors. They do not walk through the ship, they climb through it. They rappel down elevator shafts and pull themselves hand over hand along plumbing pipes that were never designed to hold human weight. In this vertigo-inducing labyrinth, the divers construct heavy timber walls. They maneuver planks of tongue and groove lumber through the submerged wreckage. They fit them between the steel decks, creating new watertight boundaries. To seal these wooden walls against the steel hull, they use underwater cement. They pour concrete into the gaps, creating a hybrid structure of wood and stone inside the steel skin. This is combat engineering at its most primitive and its most sophisticated. They are rebuilding the structural integrity of a skyscraper while it is lying on its side underwater in the dark. The risk of structural collapse is constant. As they pump water out of these new compartments, the pressure differential between the inside and the outside of the hull will be immense. If a wooden bulkhead fails, thousands of tons of water will rush into the void, destroying the balance of the ship instantly. The divers check and recheck their work. They tighten bolts by feel. They caulk seams with oakum. They are preparing the ship for the most violent stress test of her life. The weight has been stripped. The hull has been compartmentalized. The stage is set. The engineers look at their calculations and the calendar. It is August 1943. The time for preparation is over. The pumps are ready to run. It is the morning of August 4th, 1943. The preparation phase is over. The cutting torches are silent and the divers have been pulled from the water. The fate of the USS Lafayette now rests entirely on a battery of centrifugal salvage pumps. The order is given to engage the system. The silence of the Hudson River is shattered by the roar of diesel engines and electric motors. This is the moment of truth. The engineers are attempting to move a mass of nearly 80,000 tons, not with cranes or cables, but by removing weight from the inside and letting the river push the hull upward. The target is to remove approximately 11,000 tons of water from the submerged portside compartments. According to the hydrostatic calculations, this specific reduction in mass will create enough positive buoyancy to overcome the inertia of the ship. The pumps churn the black water, sending it cascading out of the discharge pipes and back into the river. The engineers stand by the inclinometers, waiting for the needle to move. They wait, and they wait. The water level inside the hull is dropping, but the angle of list remains locked at 80 degrees. The ship refuses to move. The operation has run into the phenomenon known as mud suction. The port side of the hull has been buried in the river bottom for 18 months. The weight of the ship, combined with the fine silt and sticky clay of the riverbed, has created a massive surface adhesion. The mud has formed a vacuum seal against thousands of square feet of steel plating. The hull is effectively glued to the bottom of the river. This creates a terrifying tactical problem. The pumps are generating lift, but the mud is holding the ship down. The potential energy is building up like a compressed spring. If the suction breaks suddenly, the ship could shoot upward with violent force, rolling past the vertical and slamming over onto her starboard side, crushing the pier. To mitigate this risk, the salvage team must modulate the pumping with extreme caution. They have to tease the ship out of the mud. They continue to pump, but they watch the hull gauges like hawks. Inside the hull, the water level drops inch by inch, increasing the buoyant force. Finally, the grip of the mud fails. The vacuum seal breaks. The inclinometer needle twitches. A low groan resonates through the steel structure as the metal adjusts to the shifting load. The ship begins to rotate. It is a slow and majestic resurrection. The movement is so gradual it is almost invisible to the naked eye. Degree by degree, the USS Lafayette rolls back toward the sky. The starboard bilge keel, which has been the highest point of the wreck for over 500 days, begins to arc downward. The port side of the superstructure emerges from the river, dripping with black slime and river muck. It is a ghost ship rising from the dead. But the danger is not over. As the ship rotates, the engineers must manage the critical pivot point under the bow. The rock ledge is still there. If the stern rises too fast relative to the bow, the keel will twist. The entire hull acts as a giant torsion bar. The salvage master must balance the pumping rates between the forward and aft compartments to keep the ship straight. It is a three-dimensional balancing act performed with 80,000 tons of steel. For 3 days, the pumps run continuously. The ship climbs from 80 degrees to 60, then 40, then 20. On August 7, 1943, the rotation is complete. The USS Lafayette settles into an upright position. She is floating. She lists slightly to port due to the residual mud and water, but she is vertical. The salvage operation is a complete technical success. The engineers have achieved the impossible. They have rotated an ocean liner in a crowded harbor without breaking the ship and without destroying the city infrastructure. But as the pumps wind down and the adrenaline fades, the team looks at the prize they have recovered. The ship is covered in rust and filth. The interior is a wrecked cave of rotting wood and corroded steel. They have saved the ship, but the reality of what remains is about to set in. $4,750,000. That is the final invoice for the salvage of the USS Lafayette. In 1943, that sum represents a massive investment of national treasure. It is the price of 18 months of labor by hundreds of divers engineers and naval architects. It is the cost of millions of board feet of lumber and thousands of tons of concrete. On paper, the operation is a triumph. The United States Navy has successfully righted the largest ship in the world. They have proven that the laws of physics can be bent to the will of human engineering. The ship is floated and towed to a dry dock for inspection. The salvage team hands the vessel back to the Bureau of Ships, expecting the next phase of the resurrection to begin. They expect the Lafayette to be refitted and sent to war. But when the water is pumped out of the dry dock, the cold reality of the disaster is revealed in the daylight. The hull of the great liner is a ruin. The port side plating which rested against the rock ledge for a year and a half is crushed and buckled. The physical evidence of the rock fulcrum is etched into the steel skin of the ship. The structural ribs are twisted. The stress of the capsize and the subsequent rotation has compromised the integrity of the frame. But the hull damage is secondary to the mechanical catastrophe. The 4 massive turbo-electric generators, the heart of the ship, have been submerged in corrosive saltwater and sewage. The delicate copper windings are destroyed. The complex electrical switchboards are fused masses of rust. The Naval Strategic Board looks at the numbers. To repair the hull and replace the propulsion system would cost millions more and take years of labor. The war in the Atlantic has shifted. The United States is churning out victory ships and liberty ships at a rate that makes the restoration of a single luxury liner strategically irrelevant. The Lafayette is no longer a necessary asset. She is a liability. The order is given to halt all work. The ship is declared surplus. The salvage operation, which was driven by the urgent need for a troop transport, ultimately delivers only a hull. In October 1946, the final calculation is made. The ship is sold to Lipset, Incorporated, a scrap metal firm. The price is $161,680. The mathematics of the loss are staggering. The Navy spent nearly $5 million to save a ship that was sold for less than 4% of the salvage cost. She is towed to Port Newark and cut apart piece by piece. The steel that once formed the pride of the French line is melted down to become refrigerators, automobiles, and girders for the post-war boom. Not a single soldier was ever carried to Europe on the USS Lafayette. However, to view the operation as a failure is to misunderstand the nature of salvage. The value of the Lafayette project was not in the steel recovered, but in the knowledge gained. Pier 88 became the supreme university of marine salvage. The techniques perfected in the mud of the Hudson River, the underwater concrete patching the compartmentalization, the calculation of ground reaction and pumping schedules, became the textbook for the United States Navy. The divers who learned to work by touch in the zero visibility of the North River went on to clear the harbors of Cherbourg and Manila. They opened the supply lines that won the war. The sinking of the Normandy was a tragedy of carelessness. A spark and a pile of life vests destroyed a masterpiece of naval architecture. But the raising of the Lafayette was a triumph of logic. It demonstrated that even when a machine of 80,000 tons lies dead on its side, and the laws of nature seem to conspire against it, human ingenuity can reverse the entropy. The ship is gone, but the engineering remains. The lesson is simple. Gravity is relentless, but it is not invincible.